very significant part of the University of Michigan, especially the College of Engineering. Now, my particular research with the College of Engineering was done with the Analog Research Group through the SURE program. And more importantly than what I did over the summer was the question I asked myself before applying to the SURE program. And that was, how can I, as a first-year engineering student, actually contribute to research? Well, I ended up saving the research group over $100,000 in test equipment, and I simplified the testing process they use to test the circuits they designed. So my story is probably the same as a lot of other undergraduate researchers, and that was, first, I found a professor I get along well with, and second, I found his oldest, dirtiest grad student I could find. So one of the problems they were having in the research lab was they had these big, expensive pieces of test equipment, and they needed a rather large amount of them to test one of their circuits. So I sat down with the grad student and went over some simple design techniques and how I can fix this problem. Then I taught myself some circuit design software. So I designed 2 circuit boards, I sent them off to be manufactured, and then I built them. So the end result was 2 boards that significantly helped testing within the research group. The first board I designed had 10 regulated outputs that essentially replaced 10 of the previous expensive pieces of test equipment. The second board was a bidirectional voltage translator, which essentially just makes it easier for the researchers to communicate and test their circuits. So one of the interesting things about the first board I made, the one with 10 regulated outputs, is that the outputs are actually better than the test equipment they were using.
Before going into why the board I built is better than the more expensive test equipment, it's best to go over the basic circuits the analog group designs. Analog to digital converters, or ADCs, as the name suggests, converts analog signals to digital signals. The best example would be this recording. After zooming in, you can see some discrete points. Thus my voice is stored and processed in a form a computer can save and use. Because an ADC is limited to discrete points, there will be some error between the original signal and the digital data. In graphing the error by itself, it becomes apparent there is some peak level in the ADC. So if the equipment supplying the reference levels that create the discrete points in the digital data has a larger error than the ADC's internal error, the supplied reference levels will limit the quality of the ADC. That's how the board I built is better than the larger, more expensive test equipment. As a quick example, imagine an ADC that converts a 2-volt peak-to-peak analog signal to an n-bit digital signal. After doing some math, a simple chart can be generated. The research group typically gets around 12 bits, but the reference board I built has the capability of supplying an ADC around 20 bits. Now for a few charts on noise. Under all testing setups, my board continually has better noise characteristics than the larger, more expensive test equipment.
It actually allows them to test. It actually allows them to test. Where's things? It actually allows them to test. I'm just wasting film now.